Hey guys, this is 15.9. So in this lesson, we're going to talk about change of variables in multiple integrals. So basically what this means is we're going to generalize substitution so that you probably first learned substitution U sub in Calc 1 and then you review it in Calc 2. So we're going to figure out how to do that with multiple integrals. It turns out it's a lot harder than in one variable, as if that wasn't hard enough, right? So we're going to see how to generalize this in multiple integrals. But actually, what I do want you to realize is that we have done this already. So polar coordinates and, cylindrical and spherical coordinates as well. But I think polar coordinates are a good example that or easy it's easier to keep in your head than spherical coordinates for sure. And we're going to revisit this example a little bit later, but I do want you to know that it isn't like you haven't done this before. You definitely have done this. We just didn't call it the substitution rule. And we're going to go into a little bit more theoretical background in order to see how to do this for a general substitution. Okay, so polar coordinates are a very specific substitution, but we're going to talk about how to do this for literally any possible change of variables you could possibly want to do. So we're going to start this by talking a little bit about some theory. So bear with me here, it's a lot of words. So we're going to start with a transformation. So what is a transformation? Well, basically, when you want to do a transformation, you're trying to take some, multivariate plane, so call it UV, and you want to change these variables over to X and Y, for example. Okay. So we call a transformation T, for example. And so when we plug U and V into this transformation T, we get out the variables X and Y. And X and Y themselves can be they're functions of U and V, right? Because if they weren't, how are we going to plug in U and V and get X and Y? So that's the way to think about this. Now, T is what we call a C1 transformation. This is an assumption we're making. Okay, so everything will be like this. So by C1, what we mean, so we write C with a little exponent of 1. This means that G and H, so the functions representing the variables X and Y, have continuous first order partial derivatives. So the C stands for continuous. The exponent of 1 stands for first partial derivative. Okay. Now, another way to think of a transformation is as a multivariate function. And we've done multivariate functions in this class. So a transformation is really just a fancy word for a function. The domain and the range of this function T are both subsets of R2. So, well, for us, it could be more than two variables, but that's why we're saying it transforms the UV plane into the XY plane. Okay, so it's just a function. So we've done functions before. So the other thing we want to talk about are these so you've technically done these words before, you just didn't call them what we're about to call them. So if the transformation of a point U1, V1 goes to a point X1, Y1, then we call X1, Y1 the image of the point U1, V1. So image is basically just a fancy word for Y coordinate, right? Or output. So image is just a fancy word for output, but we can't call it a Y coordinate anymore because the Y coordinate is only one of the outputs, right? We also have an X coordinate that is an output. So we use this word image instead. And if no 2 points have the same image, then we call T one-to-one. So this is the exact definition of a one-to-one function that you might have learned even in like high school algebra. I don't know. I know we definitely teach it in college algebra here. But one-to-one basically means you don't have repeated Y values, right? So to know if something is a function, you don't have repeated inputs. And if something is one-to-one, you don't have repeated outputs. And so that's what it means when it says if no 2 points have the same image. So we don't have repeated outputs. So I'll write that in red. So no repeated outputs. Okay, so what does this kind of look like as a picture? Well, let's actually draw the UV plane and the XY plane and talk about what we're even saying here, because this has been a lot of new words. So let's suppose that we just have like the first quadrant of the UV plane. Okay, so U is acting like our horizontal axis, V is our vertical axis. And suppose you've got some blob. Okay, we're going to call this blob a set S. And we've got some point in this set that is the point U1, comma, V1. Now, what the transformation T is going to do is take this plane to another plane where our variables are X and Y. Okay, so we've got a variable X, variable Y. We've got some other blob, so it's not the same blob. This is a blob R. And in this blob R, you've got some other point, X1, comma, Y1. And what the transformation T does is it says, okay, U1, V1, I substitute you in, and you become the point X1, Y1. Okay. So that is what this transformation T is doing. Remember, it's just a function. So the input is the point U1, V1. The output is the point X1, Y1 in some region R that could look completely different from the region S that you started with. So this is literally just domain and range and inputs and outputs in multiple variables. Okay, we're just giving it this different language. Now, if we have a one-to-one transformation, so if T is one-to-one, then it has an inverse transformation. So this is why in like high school algebra or college algebra or pre-calculus, we bring up one-to-one functions, because if something is one-to-one, then we can find an inverse of that function. And transformations are functions, so it's no different. So what the inverse function does, so I'll do this in red so that it's different. So T inverse would take in the point X1, Y1 and output the point U1, V1. Okay, so for an inverse, you're starting with the outputs of the original function, and the inverse function is then giving you the inputs of the original function as outputs. Okay, and so the way you would write T1 is you're trying to solve for those original input variables, U and V, in terms of X and Y. So these are original input variables, but outputs of T inverse, and X and Y are the original outputs, but now that we're dealing with T inverse, these are the inputs of T inverse. So maybe I'll put of T. There. Okay. So literally one function undoes the other. That's what an inverse is. So the classic single variable example, I think the first one you're introduced to is like exponentials and logarithms. Those are inverse pairings, as well as when you get to trig and you see all those inverse trig functions, they kind of do the same thing. Okay, so these do have some important reasons why we do them. But it turns out that this general theory is what's going to be the reason why we had to multiply by r when we did rd theta for polar coordinates. So we're going to revisit that a little later. But I just want to kind of give us some practice first with transformations in general. So we're going to look at just like transforming one region into another and seeing what these multivariate images look like. Okay. So suppose we have a transformation defined by the equations x is equal to u squared minus v squared and y is equal to 2uv. We want to find the image of the square uv such that u is between 0 and 1 and v is between 0 and 1 under this transformation. Okay, so I'm going to actually start by sketching this square on the uv plane. So I'm going to start with black because this is going to get very multicolored very quickly. So let's suppose this is the UV plane, and I want the square with side length 1. So let's see how I'm going to do this. So I'm going to start with my bottom side and make that blue. Okay, so maybe I make this blue to right here. And then I'm going to kind of make each side of this square a different color. So maybe let's make another side red. And we can make another side teal. And then maybe the last side we make pink. All right. And if I were going to label the points of this square, so we've got 0, 0. We've got 1, 0, 1, 1, and 0, 1. All right, so that's my multicolored square, and this is our region S. Okay, so all of this in here, it's a filled in square, but what I'm concerned about is that boundary. So there's a reason why I've colored each of the sides a different color. Okay, so I'm going to go through again and give these some labels. So this blue side, I'm going to call side 1, so S1. The red, I'm going to call S2, and then S3 and S4 in order there. So teal, I'm going to call S3, and finally pink, I'm going to call S4. Okay, so what I want to concentrate on is taking the boundary of this region S and applying the transformation to it. Okay, so basically what we're doing is we're taking the boundary curves in the UV plane, and we're going to apply those equations for X and Y to get new boundary curves in the XY plane. Right? So let's see how this goes. Well, first, I need to get some insight into how these curves behave. So I'm going to color code this work so that it stays interpretable when you go back and read it. So first, let's focus on the blue side, S1. So for this curve, S1, we can describe it as our V coordinate is always 0, and U lies between 0 and 1. So since these are straight, this is a straight horizontal line, our V coordinate is always 0 because it's horizontal, and it's on the U axis, and U is ranging between 0 and 1. So if I were to transform this into X and Y, well, I know that X is equal to U squared minus V squared. So if I'm thinking about what X is equal to, X is equal to U squared minus V squared, but we know that V is always 0. So X is just equal to U squared. We can say the same thing about y. So if we're thinking about plugging in that v value for y is equal to 2 times u, but v is 0. So y is just going to be equal to 0. Okay. Now, if I want to think about, you know, so I've got formulas for x and y now for this particular S1, but I also want to consider what range of values can x fall between. So let me think about how I'm going to do this. So x is equal to u squared minus v squared. Okay, so if I'm starting with my initial bounds on u, I have that 0 is less than or equal to u is less than or equal to 1. Okay, my goal, so the goal here is to make x appear in the middle. Okay, so from my work already, I know that x is equal to u squared. So the first thing that I can do is square all of the different parts of this inequality to get that 0 is less than or equal to u squared is less than or equal to 1. But since I know that u squared is x, this bounds x in between 0 and 1. Okay, so we've got 3 constraints for S1 now that we'll be able to graph. So maybe let's start drawing our graph below our original graph. So let's see. So we're going to have our XY plane. And I don't know if this is going to appear in the first quadrant or not. So I'm just going to sketch a regular old pair of axes, not really caring about the quadrant. Okay. So if I want to graph this same curve at S1 in the XY plane, okay, I know that x lies between 0 and 1, and y is equal to 0. So let's say that again. So x lies between 0 and 1, and y is equal to 0. So this is the curve S1 in the xy plane. Okay, so we're going to suppose that this point over here is 1, 0. Okay, so that's my curve S1. So far, it looks the same as the UV square. So let's do S2 and see what happens. So S2 is a vertical side where the U coordinate is always 1. So U is equal to 1. And V ranges between 0 and 1. So 0 is less than or equal to V is less than or equal to 1. Okay, so vertical side at the U coordinate 1. So now if I want to translate this into X and Y, I use those same formulas that I'm given for X and for Y. So this time I'm going to have X is equal to U is equal to 1. So I have 1 squared minus V squared. And Y is equal to 2 times U is equal to 1 times V. So X is equal to 1 minus V squared. Y is equal to 2V. Okay, so let's see what I can do with this. So, well, if Y is equal to 2V, then I think that V must be equal to 1/2 Y. So I can just divide that 2 over. But what this allows me to do is actually make a substitution in the 1 minus V squared. And I can get x as a function of y now. So I can say that this is 1 minus 1/2 y squared. So this is equal to 1 minus 1/4 y squared, which tells me that this graph is a parabola that's facing sideways. So this is a sideways parabola. Because y squared has a negative coefficient, it opens to the left. And because I've added 1 here, it's shifted right 1 unit. Okay, so if I was going to graph this function now that I know what this UV thing, S2, is in X and Y, it's a sideways parabola, or at least a portion of one where we have y ranging between 0 and 2. So how did I get y between 0 and 2? Let's think about this. So if I know that v is between 0 and 1, so let's start with 0 less than v less than 1. Well, now I know that v is equal to 1/2 y, so I can go ahead and just make that substitution there. And isolating y, I can multiply everything by 2. So 0 is less than or equal to y is less than or equal to 2. So I'm going to draw a sideways parabola, but only the portion of that graph that is between the y coordinates 0 and 2. So let's see how that turns out. So it's a sideways parabola opening to the left. It's shifted right, so that vertex is going to line up with the point 1, 0. And it's going to do this, but it is going to stop at the point 0, 2. So it's going to stop up here at the point 0, 2. So this is the XY transformation of that S2 curve. So you might notice now that S2 looks quite different than its original self under that transformation. Okay, so let's keep going with S3 and see what happens with S3. So S3 is our teal curve. So I'm going to do this work in teal. All right, so S3, we have another horizontal line, so the top of that original square. The U coordinate varies between 0 and 1, kind of like S1. But V is equal to 1 because it's the top side of the square. So the V coordinate is always 1 along that teal edge. So if I transform this into X and Y, once again, I'm going to use those formulas that I'm given. So X will be equal to U squared minus 1 squared, because V is equal to 1. So this is equal to U squared minus 1. On the other hand, Y is equal to 2 times U times V, but V is 1. So Y is equal to 2U. Now, kind of similar to S2, we can isolate U in terms of Y. So we can say that U is equal to 1/2 times Y. And just like S2, we can plug this in for U. And so we get 1/4 times Y squared minus 1, which has a similar shape. So it's still a sideways parabola, X is equal to Y squared. But this time, since the coefficient of Y squared is positive, it's going to open to the right. and it's shifted left 1 unit. Okay, so basically what we're going to get is a mirror image of the red curve over the y-axis. So I'm going to get another part of a sideways parabola that looks something like that. So this is my curve S3. Oh, we can bound y the same way or actually this time we would be bounding. Yeah, we can bound y again. So literally the same work, how we bounded y in S2, we can also bound S3, which is what makes sure that it stops at the point 0, 2. Okay. And so finally, let's look at our curve S4. So this is the left vertical side of the original square. And what we notice about S4 is that the u coordinate is always 0, and v ranges between 0 and 1. So if we're going to translate this into x and y, x is equal to u squared minus v squared. So that's 0 squared minus v squared, which is just negative v squared. Y is equal to 2 times u, which is 0, times v, which is 0. So that's y. So let's bound x. Okay, so we know that y always is 0. So this is going to lie along the x-axis. So we need to actually bound what coordinates x stays in between. So we can do this by starting with our original bounds for u again. So if we know that u are, hang on, sorry, v. We can start with our original v bounds. And we know that v lies between 0 and 1. So what do we know about this? So we want to bound x. So what we're trying to make show up is negative v squared. Okay. So first I can square every piece of this inequality. So we have 0 less than or equal to v squared less than or equal to 1. And if I multiply through by a negative, we'll have, well, negative 0 is just 0. Multiplying by a negative flips the direction of my inequalities. And so we have negative v squared is between negative 1 and 0, meaning that negative 1 is less than or equal to x is less than or equal to 0. So what this means is that S4 is going to be a mirror image of S1 over the y-axis. So S4 is this line segment between negative 1 and 0. Okay, so what we have here is our region R. So this kind of rounded triangular figure is our region R, and this would all be filled in. So this is an example of finding the image of a particular shape under a transformation. Okay, so now we're going to get to the real meat of this lesson, which I think is like, it kind of ties everything we've been doing together. So we're going to get to why did we have to multiply by r dr d theta when we did polar coordinates. And the answer to that question has to do, and also rho squared sine of phi with spherical coordinates, we had that one as well. So the answer has to do with this special matrix of partial derivatives called a Jacobian. So the Jacobian of the transformation t given by, x is equal to some function g of the variables u and v, y is equal to another function h of the variables u and v. So the Jacobian is the matrix of I said that wrong. The determinant of the 2x2 matrix of partial derivatives. Now, you could extend this into higher variables. And so finding determinants of bigger matrices is something that you will do in linear algebra if you haven't already. But for now, we're just going to look at the 2x2 case. And we have seen this before with the Hessian. That was another matrix that we saw a while back in this class. So the Jacobian, though, is very, very straightforward, literally just partial derivatives. So the way that this works is the top row, you're looking at the variable x. The bottom row, you're looking at the variable y. The first column, you're looking at the variable u, and the second column, you're looking at the variable v. Okay, so the rows are your output variables in order. And your columns are your input variables in order. And that's very important so that the calculation doesn't get messed up. But you have actually done this calculation before. So the way this works is we multiply the forward diagonal. So we multiply these two partial derivatives, and that's that term right there. And then we subtract off the product of the backward diagonal. So I know green and red in the same paper is bad practice, but we're going to do it here just to signal forwards and backwards. Okay. So again, the forward diagonal minus the backward diagonal of this Jacobian. Okay. So you are welcome to just remember the formula at the end if you want. However, for me, I think it's a little easier to set it up as a matrix. And then if you know how to do the calculation, the formula naturally falls out. Okay. Especially those of you who are in linear algebra now, or maybe you already took it, tying it back to something you already know rather than memorizing another formula is it's kind of a better way to do things so that you're not overwhelmed with so many formulas. Okay, so that's the Jacobian, and that is actually the answer to our question of why we multiply r dr d theta when we did polar coordinates. So we're going to look at how we do a change of variables in a double integral. Again, you could do this for larger and larger numbers of variables. However, we're only going to look at two because we don't know too much about doing determinants of matrices. Okay. So suppose T is a C1 transformation whose Jacobian is non-zero, and that T maps a region S in the UV plane onto a region R in the XY plane. So basically the definition of a transformation. So going back to the first page of your notes, the entire purpose of that first sentence is just to tell you what a transformation is. Okay. We're going to suppose that we have a function f that's continuous on R, and that we can do integrals on R and S. So R and S are integrable. It's pretty important to be able to do integrals if you want to do an integral. And then suppose also that T is 1-to-1, except perhaps on the boundary of S, which naturally means that we can get an inverse of T if we needed to. Then look at what we have here. So the integral of some function f in the variables x, y is so the integral of a function f in the variables x, y, we plug in the functions of u and v. Okay, so look at this here. So we've got x, and we've got x uv. We've got y, and we've got y uv. And then we're multiplying by this quantity, the magnitude, or the absolute value, depending on how many variables you're in, of that Jacobian J. So let's think about what this is in polar coordinates. So like, let's match up polar coordinates to this formula. So we know that x in polar coordinates is r times cosine of theta. And we know that y is r sine of theta. And we know that we had that weird r that we just had to put there because we were told to. And then look at that. So how I really want to convince you is we're going to actually see that the Jacobian of this transformation of polar coordinates, its Jacobian is r, okay? And this is where things really start to fall into place. So now we have a general formula to literally do any kind of change of variables that we want. So I'm going to show you the Jacobian for polar coordinates. However, something cool to do on your own would be to repeat the process with spherical coordinates, find the Jacobian of spherical coordinates, and see if you get that special integrating factor rho squared sine of phi. I bet you do, because it's the same thing, which is pretty cool. All right, so why did we have to use r dr d theta when converting multiple integrals to polar coordinates? So we already matched up the formula above, but let's compute the Jacobian for polar coordinates, which is the transformation t equal to x equal to r cosine of theta and y equal to r sine of theta, okay? So we're no longer thinking about polar coordinates as a coordinate system. We're thinking about it as a transformation of the polar plane into the rectangular plane, okay? So we're going to compute the Jacobian for t. So j, we know, is equal to xu, xv, yu, yv. Okay? So the partial of x with respect to, well, let's see, let's replace these with our polar variables. So in this case, r is u, because that's the first coordinate in a polar point, and theta is v, because that's the second coordinate in a polar point. So now I really have it written in terms of all my variables. So the partial of x with respect to r is going to be cosine of theta. The partial of x with respect to theta is negative r sine of theta. The partial of y with respect to r is sine of theta. And the partial of y with respect to theta is r cosine of theta. So now that I have all the partial derivatives in this Jacobian, I can calculate the determinant. So first things first, I'm going to do the forward diagonal. So cosine of theta times r cosine of theta, which gives me r times cosine squared of theta. And then we've got sine of theta times, all right, highlighter, come on, times negative r sine of theta. So that's going to give me negative r sine squared of theta, but I'm subtracting it. So that's going to be r sine squared of theta. And guess what happens? Y'all, this is so cool. I'm sorry we didn't get to do this in class because this is awesome. So look what happens if we factor out r. We know that cosine squared of theta plus sine squared of theta is 1. So indeed, the Jacobian for this transformation of polar coordinates is r. And that, my friends, is your answer as to why polar coordinates had that r at the back. And I told you would get your answer. It would just take a while. So I'm glad we were able to do that. Okay, so let's look at a transformation that is not polar coordinates. So we're going to look at a more general change of variables, and we have seen this one before. This is the one where we spent a while doing the image of the region S before we talked about polar coordinates a bit. So we're going to use the change of variables. X is equal to u squared minus v squared. Y is equal to 2uv to evaluate the integral, the double integral over r of y dA, where r is the region bounded by the x-axis and the parabolas y squared is equal to 4 minus 4x and y squared is equal to 4 plus 4x, where y is greater than 0. Okay, so the first thing that we're going to do is, well, we're going to do two things. We're going to sort of set up our integral, but then go compute the Jacobian and come back. So first I'm going to start with the double integral over r of y dA is equal to the double integral over s of 2uv, because that's what y is equal to, times the Jacobian of this transformation, du dv. Okay, so what we need to do is go find the Jacobian of this transformation. So J is equal to the determinant of the 2x2 matrix of partial derivatives. So we've got x with respect to u, x with respect to v, y with respect to u, and y with respect to v. So the partial of x with respect to u is 2u. So we're looking at these formulas, just so we're clear. The partial of x with respect to v is negative 2v. The partial of y with respect to u is 2v. And the partial of y with respect to v is 2u. So if I compute this determinant, we have 2u times 2u minus negative 2v times 2v. So this is 4u squared plus 4v squared. So now I can plug this in to my integral. So that absolute value of j is just 4u squared plus 4v squared du dv. And now I need to figure out the bounds on my integral. Okay, so from the previous example, we know that the transformation applied to S is equal to the region R, right? So that's the whole point, is we started with that square and we went to that weird like rounded triangle thing, okay? So what do we know about S? Well, I think we know how to bound S, and this is why we actually would want to do a change of variables. So if we go back up to that problem where we actually analyzed the transformation, the region S being a square is much easier to think about bounding than that rounded triangle thing, right? Because a square is a rectangle. I can call that an interval in X, cross an interval in Y, and I'm done. So I have constant bounds on my integral. Whereas with the region R, if I integrated with respect to that, now we're talking about two different parabolas. That's kind of icky. So I would probably need two integrals in that case. So this is just like when we talked about all of our different coordinate systems, why we usually had the motivation to go to a different coordinate system, right? It was because it made the bounds of our integral easier. And that's exactly what we want to do here. So we know from before that the bounds on that square are just 0 to 1 cross 0 to 1. So it's a rectangle or a square, right? And both intervals are 0 to 1. So the bounds on my integral then are 0 to 1 for both of my integrals. So now this is a very doable integral. Let's distribute and get to integrating. So we're going to have the integral from 0 to 1 of the integral from 0 to 1 of 8 u cubed times v plus 8u times v cubed du dv. Right? I can actually factor out an 8 here to make my work a little easier. And I can go ahead and integrate with respect to u. So I'm going to have 1/4 u to the fourth times v plus 1/2 u squared times v cubed, evaluated from 0 to 1 times dv. So this will be 8 times the integral from 0 to 1 of 1/4 times v plus 1/2 times v cubed dv, because the 0 makes both terms go to 0. And then I'm going to integrate again with respect to v. So this is 8 times 1/8 v squared plus 1/8 v to the fourth, evaluated from 0 to 1, which is 8 times 1/8 plus 1/8. Again, both terms go to 0 when I plug in 0, which basically just gives me 1 plus 1, which is equal to 2. All right. So again, I do want to stress that while this is a pretty deep theoretical lesson, you guys have done it before, right? We've done polar coordinates, we've done cylindrical coordinates, we've done spherical coordinates, all right? So you guys have done a change of variables. It's just now we're able to do it with more general things than just different coordinate systems. I mean, these are different coordinate systems, but they don't have special names like the ones that we've done before. Okay, well, that, my friends, is the end of Calc 3. Congrats.